Thank you, Rishabh. I will be covering the second half of calculus for Maths 1B. I'll be starting at 108, so I'll give you guys a break. Just as a reminder again, these slides will be uploaded onto the MathSoc website, and I know Rishabh put a lot of effort into making them, so make sure you check that out if you missed any of his wonderful presentation. Favorite maths topic? Don't really know. Yes. Also, I have to give Rishabh credit because he's also doing 1B this term, so he made the seminar while also doing the subject, which is pretty impressive. Anyway, I shall start. So I'll be continuing on with ODEs, with second order ODEs. So for first year maths, these are the only second order ODEs you deal with. They will look like this of some sort. So a second order ODE, second order refers to a second derivative. So we'll deal with second derivatives. In this course, we only have one type of second order ODE, and it will look like this. But it can also be homogeneous, or non-homogeneous. So a second order homogeneous ODE looks like this. So if you move all the y's onto one side, you'll get 0 on the other. And the property of this is that if we have two solutions of this homogeneous ODE, then if we take a linear combination of these solutions, this will also be a solution. Since if we sub them in, we get 0, and 0 plus 0 is 0. And so if we have two linearly independent solutions to this ODE, then every solution will be in the form of a linear sum of these two solutions. And this is how we find our general solution. So to find the homogeneous solution, first we substitute y equals ae to lambda x. since this is what the solution will look like. However, after subbing it in, we find that so when we differentiate, the lambda comes out. And so if we take the second derivative, we get lambda squared. And since this is an exponential, then we can just, it stays the same. And so we can factor it out. And we get this equation with the lambdas, which is called the characteristic equation. So hopefully by now you can jump straight from the ODE to this characteristic equation, because it's always the same process. And now we solve the lambdas, and there are three cases. So firstly, the first case is when we have two distinct real roots. And in this case, our solution will just be a sum of the two exponentials, so it will look like this. However, if there's one repeated root, because we want two linearly independent solutions, then we add an x to the front of the second one, and this becomes our general solution. And in the case where the characteristic equation has two complex roots, this is actually just a special case of the first case. So if you try subbing in a alpha plus minus beta alpha I into e to the lambda x, we'll find using Euler's equation that we'll get the cosines and sines. However, just for convenience, the solution will always look like this. So here, is there a reason why we add the x? Yes, there is. I think it's in the course notes, so you can look up there. But you just know that you just add an x in front. So here I have an example. So here we can see that we have a second order ODE, and on the right it's a 0, so this is a homogeneous equation. And so to solve it, as I said, hopefully you can jump to the characteristic equation. So if we jump to the characteristic equation, we get lambda squared plus 6 lambda plus 9. From this we get a double root at minus 3. And so this is case 2 when we have a double root. So we have a e to the minus 3x, and for the second one we add an x in front. So this is our general solution. And now for non-homogeneous ODEs, this is when we actually have something on the right, not just 0. But to solve this, we actually do need to find the homogeneous solution first, so we can get the general solution. Because when we have a homogeneous solution, if we sub it in, we'll get 0 on the right. So actually, if we add the homogeneous solution to a particular solution, and the particular solution is the thing that solves this, then it will also be a solution. So to find a particular solution, what we do is we make a guess by looking at the form of fx, and we'll try to match it with our guess. So this I pulled from the course notes. So if we have a polynomial, then we'll match it with a polynomial of the same degree n. If we have an exponential, we match it with an exponential. And if we have a trig, either cos or sine, then we match it with cos plus sine. There should be an x here. But anyway, notice how there's p's and q's in front of everything. This is just for generality. Remember, a constant is also a type of polynomial. So if you find you just have an exponential with no polynomial, that still counts as this case. And so to solve this, we sub in a constant times an exponential. So the general way to solve for non-homogeneous ODEs is that first we make a guess, and however, if the guess is in the homogeneous solution, that means it can't be a solution for the particular ODE, since if we sub it in, we'll get 0. So all we do is we add x in front, and if it's still in the homogeneous solution, then we add x again. And I have an example on the next slide, I think. After we make this guess, we sub it into an ODE and we find the coefficients. So before we had these q's in front, these q's are polynomials, or they can be constants. And although we know the degree of the polynomial, we don't actually know the constants. And so we have to find them by subbing it into the ODE. Then once we've found a particular solution, we add it to the homogeneous solution, and that will give us our general solution. And also, if the question is an initial value problem, then we actually need to find the constants. By this I mean the constants of the homogeneous solution, because we already have the constants of the particular solution. And we find that by subbing it in. So this is continuing on. So what form of the trial solution would you use to find a particular solution to this differential equation? So here now we have a non-homogeneous equation, and our fx is e to the minus 3x. So we would think our guess would be of the form e to the minus 3x. However, if you remember, e to the minus 3x was a solution to the homogeneous equation. We have e to the minus 3x here. And if we add an x in front, it's still in the homogeneous solution. So we add x twice, so we have x squared e to the minus 3x. And of course, remember, we need a constant in front because this alone does not fit perfectly. So we add a constant, and we would solve this constant by subbing it in. But this question just asks for what form. So here I have another example. So here it doesn't give you any steps, it just asks to find the solution. So remember, we start with the homogeneous equation, so ignore this ax and replace it with 0. We solve the homogeneous equation. So we start with the characteristic equation with the lambdas. So again, hopefully you can jump straight from the ODE to the characteristic equation. So y double dash becomes lambda squared, y dash becomes lambda, and y doesn't have any lambda. Again, so our roots will be minus 2 because we get lambda plus 2 squared. So again, we have a double root, and so our homogeneous solution will look like this. So we add an x in front of the second one. And now we need to find a particular solution. So here we have ax. So if you think about it, this also counts as a polynomial of degree 1, since this is x to the 1. So I guess will be a polynomial of degree 1. And if you look at the homogeneous solution, or a polynomial is not in the homogeneous solution, so we don't have to worry about that. So since our guess is a polynomial of degree 1, we plug that in. So remember, if it's of degree 1, we also have this constant term. So this is just a general form, and y dash and y double dash will become this. And now we sub it into the ODE. So we had y double dash, which is 0, plus 4y dash, so that's 4c, plus 4y equals ax. And simplifying, and after simplifying, we find we have 4cx, and this should be the same as the ax term, so c should be 2. And now we also have a constant term in the ODE after subbing into ODE, and we don't have a constant on the right, so this constant should be 0. So that's how we get these two. When we find c is 2, d is minus 2, and so this is our full solution with our homogeneous solution and our particular solution. Here I have another example, but I will skip this. Remember, these slides will be uploaded, so you can check them out afterwards. And so that concludes ODEs, and moving on, topic 4 is Taylor series. This topic covers sequences, series, Taylor series, and power series, I believe. Is the particular solution unique? Yes, it is. Because if you look at this particular solution, right, we found 2x minus 2. There's no constants in here, so there's no way it could be any different. So there's only one particular solution that we could have used. Okay, so to begin Taylor series, begins with classifying stationary points. I feel like this isn't examined much, but the point of this is that when we have a stationary point, which is when f dash is, when we have the first derivative equals 0, then to find what type of stationary point it is, we can use further derivatives to classify it. So well, that's the general solution. So when we have a stationary point, then we can find what type of stationary point it is by using further derivatives. So you might have learnt in high school, or maybe not, that we can use a second derivative, and that will determine whether it's concave up or concave down. So this is just a more general case. So the idea is that we keep differentiating until we get something that's not 0, because if you remember, if we have a stationary point but the second derivative is also 0, that's inconclusive. So what we do is we keep differentiating until we find a derivative that's not 0, and these are the conditions which tell what type of stationary point it is. So we have an even non-zero derivative, and if it's positive, it's a minimum. If it's negative, it's a maximum. And if we only have if we have an odd non-zero derivative, then it's a horizontal point of inflection. So moving on, sequences. So a sequence is a function with the natural numbers as its domain and real numbers as its codomain. So it's just I guess a bunch of numbers which are often defined by a rule. So it can have a direct rule like a function. So as a function, an is has some rule defined on n, or it could be defined recursively. So in this case, we don't know what it is in terms of n, but we can find it in terms of previous terms. Sequence can be convergent or divergent. So if it's convergent, that means it approaches some finite number L as n approaches infinity. And this number has to be fixed. So So a sequence that's not convergent is divergent. And a divergent sequence can either be boundedly divergent or unboundedly divergent. So boundedly divergent means it goes off to infinity or negative infinity. But it can also be... that's unboundedly divergent. So unboundedly divergent means it's not bounded, so it goes off to infinity or negative infinity. But if the sequence can also be bounded and still be divergent. So for example, in this sequence, an equals sine n. We know that sine n is always in between -1 and 1, so it's bounded. But it's not convergent because it doesn't approach a single value as n goes to infinity. If we have a rule for this sequence which applies for all large n, and if we take the limit of this function in terms of real numbers, and this limit exists, then we can say that the limit of the sequence is equal to the limit of the function. I think that's relatively intuitive. So if we have some rule and the rule is convergent, then the sequence is convergent. So here I have an example. Determine whether this sequence, or whether the sequence defined by this rule is converges or diverges as n goes to infinity. And if it converges, finds its limit. So one thing you can do is you can always check into your calculator. So just sub in some large numbers into your calculator into this. And remember, just because it's bounded doesn't mean it converges. So make sure you sub in multiple numbers to check that it converges towards a single number. And if you do that, you'll find that it approaches 0.5. although it's actually see why we can we have to look into this rule in some more depth. So if we multiply this by top and bottom by this, so it's like the rationalizing the denominator method. We multiply by this square root plus the second square root by the top and bottom, so we're not changing it. Then the top becomes, the square roots are removed, so it becomes n plus square root n minus n, which leaves square root n on the top. And then if we divide by square root n, we'll get this, which is just some manipulations. And as we take n to infinity, all this cancels out, so we get 1 over 1 plus 1, so we get 0.5, which tells us why our sequence converges to 0.5. Sequences, they can be combined by, we can add or subtract them. That just means we add or subtract the individual terms. And if two sequences are convergent, then we can do the same with the limits. So here, this table is also from the course notes. This gives us an order of different sequences in terms of their growth. So we can see that logs, so any sequence defined by log grows slowly, and if we have some sequence defined by a power, then that grows more rapidly than the log. The exponential grows more rapidly than the power, and factorials grow very rapidly. And this is important when we look at Taylor series, because in Taylor series we have a sum of powers divided by a factorial. And so since the factorial grows faster than the power, then this helps our Taylor series to converge. We also have a pinching theorem for sequences, and this is just like the normal pinching theorem. It's just stating that if we have sequences, so instead of functions we have sequences, and we have some sequence that's stuck between two sequences, and if these two sequences both converge towards a single value L, then this sequence which is stuck in between will also converge to that L. Here's a test for convergence. So it has two conditions, which is that the sequence is monotonic and bounded. And the sequence is monotonic if it's non-increasing or non-decreasing. So when I say non-increasing, it's not just decreasing, it could also be flat. But the idea is that when we look at the sequence like as a graph, then it would not change directions. So it would either go up or down, but not both. The sequence is bounded if there's an m such that every term in the sequence is less than the m, or in this case it's bounded above. And so when we have these two conditions, well, not just both conditions, but in a particular order. So we have non-decreasing sequence of real numbers. So we have a non-decreasing sequence that is bounded above, then that means that will converge. So this is a test for convergence. This is for the higher students, suprema and infima. So the supremum of a sequence is defined as the least upper bound. So there are two conditions, one being that it's an upper bound, so this supremum must be greater than every term in the sequence, or greater than or equal to. And every upper bound is greater than or equal to this m, so that m is the least upper bound. And similarly, the infimum is just the greatest lower bound. And we have this least upper bound axiom, which states that every non-empty set of real numbers is bounded above. So we can always, that is bounded above has the least upper bound. So if we have a sequence of real numbers, we can always find a supremum, as long as it's bounded above. So here I have an example, but I shall skip this. So moving on from sequences, we have series, which are in a way a sum of the terms of a sequence. So a partial sum is a sum of a sequence up to some value n. So when we have some sequence a, then the partial sum up to n is just this sum. And if we take this n to infinity, then this is what we often call an infinite series or a series. And this infinite series is summable if it converges to some value L. So that means it becomes this fixed number, this real number L. And if the series does not approach some finite number, then it diverges. With summable series, since they converge, we can treat them like regular sums. So we can add these terms individually, and we can also multiply the terms by a constant. And they'll still converge because we're just working with finite numbers in a way, since these series converge. And since finite sum will always be finite, we can always cut off a section of the sum, and that won't change whether the sum converges or not. So if we have sum from 0 to infinity, it will converge if and only if the sum from any value n to infinity converges. Because the difference between these two is the sum from 0 to n, and that doesn't change whether the sum converges or not. So this is a test strictly for divergence. So this is saying that if the terms of a sum diverge, then this series composed of this sequence will diverge. And this only tells divergence. We can't use it for convergence. So here I have an example. So suppose we have a convergent series where all the terms are positive. So first we want to ask to state the limit of this sequence of an. So for the series to converge, then we must have this equal 0. Since if this term doesn't converge to 0, then and since the terms are all positive, then we'll always be adding positive numbers, and so the series will continue growing and it won't converge. So in order for the series to converge, these terms have to eventually become 0, so that we can stop adding numbers and the series will stop growing. So this limit must be 0. For part B, asked to use the nth test, which is basically the Cave test, to show that this sum diverges. So remember, the Cave test was just we just had to show that this term diverges as k goes to infinity. So we know that if we know that this limit of an goes to 0, then the limit of log of an, well, that's the log of 0, and that goes to minus infinity. So as a sequence, since this sequence diverges, the sequence of log an, then by the Cave test, this infinite sum diverges. So that means this sum of log of an diverges. And for part C, this requires the comparison test, so to cover that first. So the comparison test states that if we have two series where the terms have this condition, so the terms of A are always less than or equal to respective terms of B, and also they're all positive, then if the larger sum converges, then the smaller sum converges. And if the smaller sum diverges, then the larger sum diverges. And that's the idea behind the comparison test. I'll cover P-series in just a sec. So going back to part C, we're given that this function is positive for x is greater than 0, determine whether this sum of log of 1 plus an converges or diverges. So when they state that this function is positive, this is giving a hint that we can use some form of the comparison, or we can use the condition for the comparison. So if we rearrange that, then we know that since x minus log of 1 plus x is positive, that means x is greater than log of 1 plus x. And since this is since x is positive, then this log is also greater than 0. So this is the condition we need to use the comparison test. So now we can use the comparison test. If we sub in an, then we get this. Since an is all positive, then we can use this because we know that the terms an are all positive. So we can sub in an, and this condition still holds. And now by the comparison test, if we take the sum of an, this sum, and we know that this sum converges, then the sum of the smaller terms will also converge. And so by the comparison test, the sum of log of 1 plus an converges. And so a P series, they refer to sums of this form. So when we have 1 over the term to the power of P, this series will converge if P is greater than 1 and will diverge if P is less than or equal to 1. And this is a very simple test, but it's quite important because it allows us to compare things quite easily. Because we know anything from this, because if we have anything of this form, then we can know immediately whether it converges or diverges. And so here I have a simple question. So state whether this is true or false. So whether this so does this series diverge? Well, this is just a P series and S is 2/3, which means it's less than 1, so that is true. So S is less than or equal to 1, which means this will diverge. So this is for the higher students, which is the limit form of the comparison test. So suppose we have two sequences which are positive. And note that many of these tests require positive sequences, and this is also one of them. So suppose we have two positive sequences, and when we take the ratio of the sequences, and we take the limit of these, so as n goes to infinity, and this ratio equals some L, where L is a non-zero finite number, then both these series either both converge or they both diverge. I haven't actually seen this come up much though. This is the integral test. So this one is quite hopefully relatively intuitive, because if you know the relationship between sums and integrals. So if we have some formula, we can replace it with a function. And if this integral well, the function also has to be positive. So the function must be positive and decreasing. And so if this integral converges, so if it's equal to some finite number, then the sum also converges. And if this integral diverges, then the sum also diverges. Next we have the ratio test. So this is just saying that when we have an infinite series, and again these terms must be positive. Yes, that's does. Anyway, suppose we have some series with positive terms, then if this we have this, and we can find this ratio as k goes to infinity, and it's equal to some value r. Then if this r is less than 1, meaning that this series is decreasing, then the sum will converge. And if the ratio is greater than 1, then the sum will diverge. However, if we find that r equals 1, then this test is inconclusive, which means we don't actually know. I mean, you can integrate non-continuous functions. They just have to be, but they have to be they have to be able to be integrated. But I'm not so sure about that. So using an appropriate test, determine whether the following series converges or diverges. So for part A, we have this sum n squared over 2 to the n. And now this is when we have some power 2 to the n, then that's looks nice for a ratio test. So we try the ratio test, and also by inspection we can see that these terms are positive, which means we can use the ratio test. So we use the ratio test. We take the limit as n goes to infinity of a to the n plus 1, which is n plus 1 squared over 2 to the n plus 1 over an. And then we can simplify it. So the 2 n's, so 2 to the n cancels out. We're left with 2 to the 2 on the bottom. And so we're left with n plus 1 squared over n. Over n squared. So we get this limit. And since we have n squared terms, these 2 to n plus 1 becomes insignificant, and so our limit becomes 1 over 2. So that means our ratio is 1 over 2, which is less than 1. So by the ratio test, this series converges. For part B, we have this sum 1 over k to the log k squared. So here this looks like something we can integrate. Again, this is positive, and also this, if we look at it, then it's also decreasing. So we use the integral test, we integrate it, and hopefully you're comfortable with substitutions. So, okay. So we make the substitution u equals log x, and we find that 1 over x is just the derivative of log, so that becomes du. So when we integrate it, so when we make the substitution, it becomes du over u squared, and that just becomes minus 1 over u. And so when we integrate it, and this becomes 1 over log 3, which is finite. So by the integral test, this converges. So what happens when we don't have series that have only positive terms? Well, I don't think you deal with it that much. But one form is an alternating series, which is when we have, so we have alternating signs. So if all these a's are positive, then the series will look like this, where we have positive, negative, positive, negative. And they have to be strictly alternating. They can't just have some positive and some negative terms. They have to alternate between positive and negative. And if we have this series, then we test for it using Leibniz's test for convergence. And this test has 3 conditions. So if we look at the positive terms, firstly, they have all the terms. If we remove this, if we ignore these minuses and pluses, these terms all have to be greater than or equal to 0. So this is just saying that it's actually alternating. It's not just doesn't just have some positive and some negative terms. They have to be alternating between positive and negative. The second condition is that they have to be decreasing. So a to the k must be greater than or equal to a to the k plus 1. And thirdly, this sequence must converge towards 0. And when we have alternating series, we also have absolute and conditional convergence, which are 2 forms of convergence. So a series is absolutely convergent if so we take the absolute value of these terms, and this is convergent. Absolute convergence is stronger than convergence, so that means if we have absolute convergence, we also have convergence. However, if the series converges but does not converge absolutely, So for example, if it passes Leibniz's test, but it doesn't converge absolutely, then we call it conditionally convergence. And this is an interesting property in that conditionally convergent series can converge towards any number. It doesn't converge towards a fixed number. But an absolutely convergent series will have a unique value to which it converges. So now we have this series. However, unlike before, it was okay. So firstly, we have a convergent series. We have an alternating series. So the first thing we would do is to apply Leibniz's test, because that's usually not too difficult to use. And if it fails Leibniz's test, then we can say it diverges immediately. So we don't have to worry about absolute conditionally convergence. So apply Leibniz's test. First, if we ignore the minus 1 to the n, then yes, these terms are all non-negative, because for n, since n is going from 2 to infinity, then these logs will always be positive, and n is positive, so yes, that passes. Secondly, we have to show that it's decreasing. So we take a term, so we take an plus 1, that's 1 over n plus 1 log n plus 1. And since these are both increasing in the denominator, then that means they're decreasing. So if we take it down from n plus 1 to n in the denominator, that will make the function bigger. So this just shows that this term is decreasing. And thirdly, if we take the limit, yes, this goes to 0. So it passes Leibniz's test. That means the series converges. So now we check for absolute convergence. So now we have to test whether this converges. And this looks similar to before, so we can use the integral test again. But now here we have log on the bottom instead of log squared. So that becomes 1 over u. And when we sub in the bounds, well, when we integrate 1 over u, that becomes log u, which is not bounded when n goes to infinity. So this integral is not finite, which means it fails the integral test. And so this series does not converge absolutely, which means it converges conditionally. Moving on, so we have Taylor series. So Taylor series are infinite sums, which we use to approximate smooth functions. And when I say smooth, I mean, it just means they're infinitely differentiable. But yeah. So if Taylor series, they look like this, and when we expand it out, so it's just the sum of the function to the nth derivative, so that over n factorial times this power of x minus a to the n. And the point of these Taylor series is that by looking at these in terms of polynomials, well, actually that's for Taylor polynomials, they become easier to understand, because we can always work out the, like when we have a function in terms of these in terms of this sum, it becomes easier to work with. So a Taylor polynomial is a Taylor series that's cut off at some point. So it only goes up to degree n. And we define it in this form, so it's the same formula but up to n instead of infinity. And now Taylor's theorem states that when we have a function that has n plus 1 continuous derivatives on an open interval I containing a, so when we find Taylor series in Taylor polynomials, we find that around some point a, and it only works if the function is smooth around a. So there's a range in which the Taylor series works, which I think I'll get to later. So if we have this function which has n plus 1 continuous derivatives, then we can approximate it using a Taylor polynomial. And when we approximate it, we get this error which looks like this. However, this is a bit messy and hard to compute, so another form of the remainder is the Lagrange form. And the Lagrange form of the remainder will be this, where c is some value between a and x. And if you look at this, term, it actually looks like another term of the Taylor polynomial. So we have n plus 1 derivative of f divided by n plus 1 factorial times this power to n plus 1. However, instead of x, we have c, which is some value between a and x. And we don't necessarily know what it is, but we know that the remainder will be equal to this. So this was an example from last term. Hopefully some of you doing 1241 will have had a look at this since it's on Maple. So we have some polynomial of degree n. Using Taylor polynomials, we can always write it as this, which is a power series, but also so explain why we can express a polynomial in terms of a Taylor polynomial. So firstly, we'll use Taylor's theorem, right? So we know that P is a polynomial, which means it's infinitely differentiable, because if we keep differentiating it, eventually we'll get a constant, and then if we differentiate that again, we'll get 0. However, just because it's 0 doesn't mean we can't keep differentiating it. So it will always have continuous derivatives up to any power, which means we can always approximate it using a Taylor polynomial. However, in particular, this polynomial is of degree n, which means if we take the n plus 1th derivative at any value, we'll get 0. And now we can use the Lagrange form of the remainder. So if this derivative is 0, that means using the Lagrange form, the remainder will be 0 when we have m greater than n. Which means whenever we have m greater than n, then the Taylor polynomial will be equal to the polynomial, which is why we have equality rather than just an approximation. Second part asks to give an expression for the largest m for which this term is not equal to 0 in terms of n or p, and also explain how these numbers are obtained. So these two parts are kind of connected. And if you think about it, we have a degree n polynomial, so it makes sense for us to use it for m to equal n, since we're equating a polynomial to a polynomial, so it would make sense for them to be of the same degree. So we want m to equal to n for us to not have any extra terms. And for a to the I, well, that's just the term in the Taylor series, so it's just the ith derivative of p at c, since we're taking the polynomial at c and divided by the ith factorial. So a Taylor series for a function about a, so remember we have to find that it is defined about some point a, is a Taylor polynomial as we take n to infinity. And where a equals 0, this is also called a Maclaurin series. So Taylor series, or in this case, a Maclaurin series, will look like this. And if this remainder will equal 0 as n goes to infinity, that means that the Taylor series will equal the function, which means our function can equal this Taylor series. So here I have some examples of Taylor series. This is also from the course notes, but this is useful because finding Taylor series, finding these terms is a bit of work. So if we can jump to these ones that we already know, then it saves a lot of work, basically. So notice how there are restrictions on where we can approximate them. So this is just stating where this Taylor series applies, because remember the remainder is only the remainder only applies for terms for values between in some range. So when we're outside this range, then we can't apply this Taylor series. However, for functions like e to the x and these trig functions, the range is infinite. So we can use this for any x. And now a Taylor series is a type of power series, which is a sum of integer powers of x. So a power series just looks like this. It's just a series of powers. And we have some, they also have some sequence of coefficients in front of them, which determine what the power series actually looks like. So like any series, a power series can also converge or diverge. However, now we also have some variable x. So because we have this x, then the convergence or divergence will depend on this x. And when the power series is in this form, then we can say it converges within some interval. Then this interval is called the radius of convergence. And the interval is called the interval of convergence. And the radius, this radius r is called the radius of convergence. And so to define the radius of convergence, we just take this limit of the coefficients. And so we take the limit of the absolute value of the ratio between these coefficients, and we will get some ratio. We get some ratio r, and this will be the radius. However, this will give us an open interval. So this will give us an open interval, a minus r and a plus r as the interval. However, what happens at the endpoints, we have to check manually. So I have an example of this. Yes. So find the interval of convergence for this power series. So we find the limit of, so in this case, the coefficient is 1 over 3 to the n plus 1. So find this ratio of an over an plus 1. And we'll see it becomes this. And we can ignore the 1 since we're taking a limit, which will give us 3. And so our radius of convergence is 3. And since our a is 3, then our interval of convergence is 3 plus minus 3, so from 0 to 6. Now we test the endpoints, so we do that manually. However, if we look at these two series, we can see that these terms, they don't approach 0. In fact, this one alternates between, as n goes to infinity, these terms alternate between minus 1 and 1, or this one goes to 1. And since in either case, we won't have convergence, since if we keep adding these terms, the sum will never go to some fixed value. So the series does not converge at the endpoints, and so our interval of convergence is an open interval from 0 to 6. It's open, right? Power series can be manipulated, which is what makes them useful. So when we have some power series, we can differentiate them or integrate them. And to do that, it's just taking the derivative or integral of the individual terms. So if we differentiate each term, the k will come out and the power goes down. Although when we differentiate it, we lose the 0th term, so the sum goes from k equals 1. And similarly, we can integrate these. And so from this, we can say that any function that can be expressed as a power series is continuous and differentiable, since these power series are always continuous and they're always differentiable within the radius of convergence. So here I have a question. Write down the Taylor series for sine x squared about x equals 0. Going over time a bit. apologize for that. So to write down the Taylor series, well, we can differentiate them. We can keep differentiating and use the formula, but that's a bit of a work. That's a bit of work. So we can instead use the Taylor series we know for sine x, which looks like this, and we know that this series works for all x. So we can just plug in x squared, and the Taylor series for sine x squared will look like this as a result. And the question also asks to state the radius of convergence. Well, we know the Taylor series for sine, the radius is infinite, and so that will be the same for sine x squared. So this radius of convergence is infinite. And then now part B asks us to find the integral of this sine x squared using the Taylor series. So the Taylor series is a type of power series, and so these can be so to integrate it, we can just integrate the individual terms. And so when we integrate it, we move the integral inside. And now when we integrate this, well, this is just, remember k is just a constant, so this is just x to some power. And so we can integrate this, and we'll find that the integral is equal to this sum. And that's the end of Taylor series. So moving on to the last topic, which is application of integration. Although this topic is quite short and really just a bunch of formulas if you don't want to look into it too deeply. So firstly, we're given that the average value of a function is defined as basically the integral divided by the width of the integral. That's all there is to it. And the mean value theorem for integral, this is a version of the mean value, but a version of the mean value theorem, but instead for integrals. So suppose we have some continuous function f, then when we integrate it from a to b, then this integral will be equal to this function times b minus a for some c inside this inside this interval from a to b. And we can connect this to the regular mean value theorem by expressing little f as capital F, where capital F is the antiderivative of little f. So if we express this in terms of capital F, we know that from the fundamental theorem of calculus, we can write this as capital F of b minus capital F of a. And if we move the b minus a over, and little f is just the derivative of capital F, then we can express it as the regular mean value theorem, but in terms of capital F. And so that's the connection between the two. So here come the formulas. So firstly, when we can calculate the arc length of a curve, and actually it's just a formula. So there are three formulas depending on what type of, depending on how you are given the curve. So in parameterized form, which is where we have the curve where x and y are in terms of t, then the arc length is just this integral. The square is integral from a to b, or the square root of x dash squared plus y dash squared. For us to use this, it's important that the path does not retrace its steps. For a function, then the formula is this. Since the exam is open book, I think this part shouldn't be too difficult, because you can always just pull out the formulas if you need them. But just be aware that these formulas exist, I guess. So in the function form, the form looks like this. So in this example, we have a function cosh of x, which is in between. So that's a function for cosh of x between a and b, and we let L be the arc length and a to be the area. So the question asks to prove that the arc length of cosh between a and b is equal to the area under the curve from A to B, which is an interesting property. So first we start with the arc length. So here we have in function form because we have the arc, we have y in terms of x, or in this case h of x in terms of x. So we apply the formula, which is just the integral from a to b of square root of 1 plus f dash, or h dash in this case. And remember, the derivative of cosh is sign, not negative sign, but sign. And now this is another property, cosh squared minus sign squared is 1. So if we rearrange that, 1 plus sign squared is just cosh squared, which means this becomes cosh squared, and if we take the square root, it's cosh. And now this is, hopefully you can see, it's just the area. So the area is under the curve from A to B, is just cosh squared. I'm sorry, cosh. So you have to memorize the integral. Yes, fam. No. So, you can always pull out the integrals in the middle of the exam, I guess, if you need them. And so these two, the arc length is equal to the area. And now if we have it in polar coordinates, well then the arc length is just this. And polar coordinates is when we have in terms of r and theta. So next then we have the surface areas. So again, these are just some formulas. So they don't look too nice, but they're also not too bad. And if you look at them, the relationship between them, you might be able to see that they do resemble each other. So when we have in parameterized, so these formula are for when we have a curve and we rotate it around the x-axis, then the surface area will be given by these formulas. So we have it in parameterized form. So if we have x and y in terms of t, then our surface area, when we use the first formula, we have in function form, so in terms of x, then we use the second form, and for polar coordinates, we use the third form. So here we have our question. So the surface is formed by rotating this curve around the y-axis. And what is its surface area? So here we have, in terms of x, although actually this curve asks to rotate around the y-axis. So which means we need to switch it, we need to change it in terms of y. So we change the formula in terms of y, so x becomes square root 4y plus 1. And we take the positive square root because we want the curve to be positive. That was... Okay, I didn't write that there. But if we take the negative, we get a negative surface area. So that's why we take the positive. And now, remember, we also need to change the bounds. So we find the bounds by subbing in 2. So 2 squared over 4 is 1, 1 minus 1 is 0. And we sub in 3, we also get 5 over 4. So this is our bounds. This is our formula. And for our formula, we also need f dash. So the f dash is just this. And so this is our formula. And then now, this integral might not look too nice, but it's not actually not too bad. So if we take out the constants and we rewrite this 1 plus 1 over y plus 1 as y plus 2 over y plus 1 by moving in the y 1, then we can cancel out the square root 1 plus y plus 1 in the denominator, and we get this square root. And we can integrate it, and we find that the surface area is equal to this. And that is the end of, no one has any questions, that is the end of the seminar. So thank you all for attending, I guess.